Now, today we are dealing with constraint optimization problem. This is a general form of constraint optimization problem. Find the decision vector x where we want to minimize, that minimizes function f x subject to the constraint g j x less than equal to 0, h k x equal to 0, and the decision vector is having n components, decision variable vector. Now, here we have considered the m number of inequality constraints, p number of equality constraints. Now, this constraint set divides the whole design space into two parts. One part is the feasible space, that is the decision space where the constraints are being satisfied, and the other space where the constraints, at least one of the constraint is violated, that is the infeasible space. Now, in the decision space, that is in the feasible space, our target is to find that x which minimizes f x. Now, there are since these are functions, we have considered the functions f x, g j x and h k, these are all nonlinear in nature, and due to the inherent complexity of the nonlinear functions, it is not so easy to find out the optimal solution in the decision space. Now, in this connection, let me tell you few things, that is in the feasible space, if some constraint particular j is being satisfied with the equality sign, then it is said to be the active constraint. Rather, if the optimal solution exter is on the sum of the constraint, then corresponding constraint is said to be the active constraint, otherwise the constraint is inactive. That means that in the decisions process, that constraint is not taking part for achieving the optimal solution. That is the idea of the active constraint and the inactive constraint. For the inactive constraint, thus it is being satisfied with the lesser than sign, that is the idea. Now, we know how to solve it. For solving this kind of problem, as we know, the first technique is that KKT conditions. Through the KKT condition, introducing the Lagrange multipliers, we can solve this problem. Other than this, there is a set of methods are available. The methods can be categorized into two parts. One is the direct method and another one is the indirect method. Direct method considers the problem, the given nonlinear problem in an explicit manner, whereas in the indirect method, the given nonlinear problem is being solved by a sequence of unconstrained minimization problem for this minimization nonlinear problem, and that is the indirect method. Direct method, there is a list of direct methods are available. One is that heuristic search method. Few of them I will discuss today. Constraint approximation method, that is the cutting plane method suggested by Kelly. And there is another set of methods that they have available, that is the methods of feasible direction. In this set of methods, there are two methods are available. One is that Zaudendijk feasible direction method, and second one is the Rosen's gradient projection method. And in the indirect method, there is also a list of indirect methods are there. By transformation of variable, we can solve the given nonlinear programming problem, and other than this, there is a set of penalty function method. In the penalty function method, there are two kinds of penalty function methods. One is the interior penalty function method and another one is the exterior penalty function method. Thus, we will discuss both the types, the direct method and indirect method in detail. Let me start with the direct method today, and let me start with the constraint approximation method. That is the, in other name we can just name it as a Cayley's cutting plane method. This method is a very nice method in this sense that the objective, the basic philosophy of this method is that the nonlinear functions f x, g j x and h k x, these are in the nonlinear form. Now, it is all the nonlinear functions are approximated with the linear functions, and a sequence of linear programming problems are being solved, and at the end we will reach to the optimal solution of the original problem. That is the idea. Now, for this thing, let me consider a problem again, minimization of f x subject to g j x less than 0 and h k x equal to 0. Now, the step 1 is that this is a sequential process we will just adopt. We will start from a point x 1, where point x 1 need not be feasible point. Now, and let us set the iteration number as I is equal to 1. Now, the step 2 is that at this point we will just linearize the functions f x, g j x and h k x with the Taylor series approximations. Once we are doing that, what is happening that we are having the nonlinear feasible space, rather the feasible space bounded by the nonlinear functions. Now, we are approximating this nonlinear feasible space with the linearly bounded feasible space. And once we are considering the point x 1, which is not even the feasible point, need not to be a feasible point, then the linear feasible space, rather the feasible space bounded by the linear functions, that would be the outside of the original nonlinear feasible space. That is the idea. That is why let me just elaborate the process a little more, then it will, then you can understand it. What we do, we will just linearize the functions at x 1 using Taylor series approximation. Thus, we can write that f x can be approximated equal to f x 1 plus del f x 1 t x minus x 1. Similarly, we can write g j x is equal to approximately equal to g x 1 g j x 1 plus grad of g j x 1 t x minus x 1. Similarly, h k can be written in the similar manner, that is with the Taylor series approximation, we are just writing it. This is h k, sorry, grad of h k t x minus x 1. Now, once we are doing that, that means, let me, here we have ignored the higher order terms, because we have to ignore, because we wanted to linearize, we wanted to have the linear functions. If we want to approximate with the quadratic function, then we will take the second term as well. That is the idea. Now, if this is so, then we can reformulate the given problem. This problem can be reformulated again with minimization of f x 1 plus grad of f x 1 t x minus x 1, rather let me just do it subject to this set. Say this is the set A, all right. And once this is so, it is very clear this is a linear programming problem, and we can solve this linear programming problem and we will get the optimal solution. Now, you see whatever optimal solution we will get for this problem, that optimal solution would be outside of the feasible space of the original problem. Once again I am just repeating the thing. You see, we have taken a feasible space, the original feasible space is bounded by the nonlinear functions. Now, we have approximated each functions with the linear functions. That is why, since the point about the point x1 is in the outside the feasible space, thus the approximated linear programming problem will have the feasible space which will outside the feasible space of the original problem. Thus, as we know that always the optimal solution for the linear programming problem would be in the boundary and it is in the extreme point. That is why whatever optimal solution we will achieve here, that would be the point that lie outside the feasible space of the original problem, that I wanted to say. Now, once we are getting the optimal solution, that optimal solution may satisfy all the constraints or may not satisfy all the constraints. If it satisfies all the constraints, then that optimal solution can be considered as a optimal solution of the original problem. That means, whatever optimal solution we have achieved from this linear programming problem, that is within the feasible space of the original problem, but it is not happening as such because x1 is not really at the feasible point. Now, if it is not being satisfied, then we have to adopt the next process. That is why let me move to the step 4. When Gj(x1) is greater than a very small number epsilon, because in general we know that Gj(x1) is lesser than equal to 0. That is why if x1 is being satisfied, is not x1, let me consider the optimal solution we are getting out of it, that is x2. That is why we will just substitute x2 in all inequality constraints, and if we see that it is satisfies, then Gj(x2) must be lesser than equal to 0, but if it is not lesser than 0, that means that Gj for some j, Gj(x2) is greater than epsilon, that in that case that problem cannot be considered as a optimal solution. That is why we can write down the other logic as well. If Gj(x2) is less than epsilon, then x2 would be the optimal solution of original problem. We can approximate origin and NLP. Otherwise, go to this step, that is the idea. Once this is so, then if we see some Gj(x) are not satisfied, are violated, then we will calculate, we will just see in step 5 most violated constraint. We have to identify that. Mathematically we can say that we will identify that j which is maximum of all Gj(x2) and such that Gj(x2) is greater than epsilon. That means, we are considering those constraints which are violated, and we will consider the most violated constraint by considering the max of this. Once we are getting that, then we will in the next step we will linearize the corresponding Gj(x prime) about x2. That means, we will get another linear constraint of this. Thus, it will become Gj(x prime x2) would be approximately equal to Gj(x2 prime x2 plus grad of Gj prime x2 and x minus x2, and we will add this constraint in the previous linear programming problem. That means what? We are we are just reconsidering the whole space, feasible space. The original linear feasible space was A, now we are adding another constraint, this constraint. That means, the feasible space is being reconstructed and we will get an optimal solution for that linear programming problem as well, and we will repeat the process. We will repeat the process in the similar manner. We will check whether all the constraints are being satisfied or not. If these are being satisfied, we can declare the next optimal solution as the optimal solution of the original NLP. Otherwise, we have to repeat from step 4 to step 6 again and again, and we have to identify in each case which constraint is being violated. In that way, we will just proceed and we will get the optimal solution at the end. Thus, we can say the next step, step 7, if we just want to complete this iteration process. Previous LPP and get optimal. Then go to step 4. Otherwise, go to step 4 how? By setting I is equal to I plus 1 . Otherwise, select the optimal. Now, what is the advantage of this process is that if I just look at the whole process once again, if I just want to summarize the process, the advantage is that this is like a Go-Morris cutting plane method we are using for integer programming problem. Here also the same thing, we are just adding the linear constraints one after another in the original feasible space, and the advantage is that we can use the simplex algorithm rather the dual simplex method, because in each step we are adding one constraint at each time, and we can use the dual simplex method very easily and we will get the optimal solution of the original problem, which is very complicated maybe, that is the nonlinear programming problem. And there is a disadvantage as well. Disadvantage is that, and this method works only for convex programming problem, because for convex programming problem only we can ensure the convergence of the process, otherwise in many cases it may diverge. And another disadvantage we can just point it out, that is that since we are adding the constraints again and again, there is a chance to become the problem as a big one, and though we can solve it with the linear programming problem, that is not a problem for us. Let us apply this method for a numerical problem, then it would be clear to you. Let us consider a nonlinear programming problem, that is minimize f x1 x2 is equal to x1 minus x2. We have considered the linear objective function, that does not matter, we can consider nonlinear as well, and there is only one constraint G, that is this problem I have taken from the optimization book written by S.S. Rao. This is the constraint for us, and it is and if we just if we want to solve it in otherwise by using the Kuhn-Tucker condition, we will see the optimal solution will be x1 star would be is equal to 0, x2 star would be is equal to 1, and f mean would be minus 1. Now, we will use the cutting plane method and we will see how the problem can be solved. Now, if we see the feasible space for this, the feasible space may be unbounded, and thus we want to bound it. That is why in the step 1, let us consider another set of constraints, that is x1 is in between minus 2 and 2 and x2 in between minus 2 and 2, these are given. Now, first what we will do, we will solve minimize f, that is x1 minus x2 subject to these two constraints, and we will see that we will get the optimal solution. That would be the starting point of our problem. X1 star would be is equal to minus 2 2, and we will get the f value at this point, f x1 star is equal to minus 4. Now, once this is so, we will just in the next step we will linearize g about x1 star. That can be done very easily. First we will find out the grad of g. Grad of g would be is equal to six x1 minus 2 x2 and minus 2 x1 plus 2 x2, and we will consider this grad of g at the point minus 2 to 2, minus 2 and 2, and then ultimately we can linearize it with the function g x1 x2 would be approximately equal to, that is g of x1 star plus grad of g x1 and x minus x1. If we just do it, we will get this value as approximately equal to minus 16 x1 plus 8 x2 minus 25. And since this is the approximated linear function of the given nonlinear function, let us consider the next step with this constraint. Thus, in the next step we will consider the next linear programming problem as minimization of x1 minus x2 subject to this constraint plus this minus 25 less than equal to 0 and x1 and x2 both minus 2 to 2. Because we wanted to bound the feasible space, that is why we have considered this constraint. Not only that, this constraint helps us in finding out the initial starting point even. Now, we will solve it, and once we will solve it, we will get the next optimal solution x2 star, that would be is equal to minus 0.5625 and 2, where the functional value would be is equal to minus 2.56. Previously it was minus 4, in the next we could see the functional value has decreased. That is why if we go further iteration, there is a chance to converse the process, but if we just see, then we will see that again that here the value of g x2 star, that is very high, it is giving 23. If I just summarize the whole process in the table, we can see it. This is the initial step for us, as we have considered minus 2 to 2, and here the gj value was 23. Now, in the next step we have considered this constraint, we got this optimal solution, we could see the functional value is minus 2 as I showed you, and then we will see again the gj value is coming very high, that is 6. That means we are still, this value is very high, that is why we have to consider we have to linearize this gj with respect to this point again. Otherwise, we will be very far from the boundary of the feasible region, original the given problem. That means, once we are linearizing gj with respect to this point, we will get this constraint, and in the next problem we will add this constraint again. That means, we will add this constraint here itself, and once we are adding this constraint, we will get another point, that would be point 2 and 2. Functional value is again decreasing, Gj value is decreasing again and again. Thus, we will just repeat the process again and again 10 times. We could see that functional value is converging to -1 and Gj value is almost 0 here, that is why that is quite acceptable. And as we see in the original, if we just apply the KKT condition, there also we could see that the F min value was coming -1 and the corresponding optimal solution was coming 0, 1. Here also the same thing, that we are getting the optimal solution as 0, 1, almost 1. That is why this could be taken as the approximate optimal solution of the original nonlinear programming problem. And that is all about the cutting, the Cayley's cutting plane method, through which we are getting the sequential linear programming problem, and we can solve the problem with the dual simplex technique. And very nice, this method is nice in that sense that we need not to tackle the nonlinear functions at all. Very easily with the linear functions only we are getting the solutions, but disadvantage, as I said, that it is applicable for the convex programming problem. For the non-convex problem, it is not easy to consider. Now, let me go to the next method, that is the method of feasible direction. This is another direct method because we are considering the problem, we are addressing the constraint, original constraint set, original problem. Thus, this is not an indirect method, but what is the basic philosophy of this method? Let me just first summarize it, then I will go to the algorithm of this method. The method says that minimization of f x, let me consider the constraints g j x, that is the nonlinear inequality constraints, where f and g are all nonlinear functions. In the similar manner, there are m number of inequality constraints are there. Now, the method of feasible direction, there is a beauty of this method is that this is also a searching technique. We will start from a point and we will iteratively we will proceed in such a manner that functional value is decreased in each iteration. Not only that, we will remain in the feasible space. That is the idea of the method of feasible direction. And the mathematician Zaudenzik invented this method, and this method is very robust method, and this method is applicable very much, and we are using this method here and there for nonlinear programming problem. Let me just elaborate that method for you. Now, as we have seen in the KKT condition, that if we start from a point x 1, then if this point is a regular point, rather the feasible point, then that feasible, if I want to move to the next feasible point, then the idea is that we have infinite number of directions through which we can do, because as we have seen for the unconstrained optimization technique, we have adopted this process. We started from xk and we are moving to xk plus 1 with considering lambda k as the step length, and this is the direction. That means, from one point, if this is a point for us, we are moving to the next point with a specific step length, and there is a specific direction. That means, xk is going to xk plus 1. Since this is xk, we can proceed in different way. In infinite number of directions we are having, in which direction shall I move? Zaudenzik has suggested some technique. He has said just move through the usable direction, then we will reach to a better, we will adopt a better path. That is the idea. Now, let me tell you what is that. As we know that if I move from a point xk to the next point xk plus 1 with the direction s say, then we can say that s is a feasible direction. If you remember, we have done that in our KKT condition, when we have described the KKT condition in detail, we have said that this direction would be this dot product, that is if this is the feasible direction S, and if the grad f is the gradient of the objective function, always it makes the obtuse angle, that means lesser than 0. Not only that, we have also considered, to remember that ST grad of Gj is always less than is equal to 0, that also makes the obtuse angle for the minimization problem. Now, Zaudensik, he said that this direction is being, this is the feasible direction. If I move with this condition, it is a feasible direction, and if I move with this condition, that no, sorry, this is not the feasible direction, that is the descent direction. That means, for the minimization problem, if I consider the direction as S, and if we consider ST grad f, if it is giving the lesser than value, that means if it is making the obtuse angle, that if the direction makes the obtuse angle with the gradient of the objective function, then that is the descent direction. That means that direction gives me better functional value for the minimization problem. That means the functional value improves, we are getting the better minimum in this direction. Not only that, if S is the direction, if we consider ST grad Gj, where j can run from 1 to m, now this direction is the feasible direction, then it makes again the obtuse angle, and this is called the feasible direction. And he has suggested that if any direction consider both the conditions together, that means any direction S which is descent as well as feasible, then that direction can be said as the usable direction. Thus, according to Zaudensik, he has suggested that always move in that direction where the direction is usable. Alright. Let me just whatever philosophy I said, let me summarize whole thing mathematically. Now, how far we can move, that is the next question, because if I move by considering both the conditions together, then from here this point I will go to this point, then I can go to this point, then I will go to the boundary of the feasible space. In this way I will move, but we know if this is the objective function for us and optimal will come here. That is why, and that is a KKT point, and at KKT point we will see that these will all satisfy with the equality sign, that part we are just considering in the next. Before doing that thing, let me consider a minimization problem, and let us try to visualize what is the usable direction, what is the meaning of that. Plus x2 greater than equal to 4. If we just draw this one, then we can see that this is the circular region and this is the line for us and this is the circle. And if I just move further, this is a circular region, do not mistake it. Then the optimal will come here. Here is the optimal solution. Alright, because we have considered the constraint x1 plus x2 greater than equal to 4, that means this region. Now, minimization problem. Now, here mathematically we can say that, let me see which direction it is, grad of f, it is 2x1, 2x2, grad of g equal to minus 1, minus 1. If we consider the function g as minus x1, minus x2 plus 4 less than equal to 0, because I was trying to explain the methodology with g lesser than equal to 0. That is why grad g would be minus 1 in this case. If this is so, then we will say that this is the descent direction for us, and what it would be? If I consider the vector S1 S2 is the direction, then it would be 2 x1 2 x2. Let us start the process with an initial point x1 1.45 2.55. This is very much satisfying the constraint. Let this is the point for us. Then we can see that ST grad f for this point, it is coming as S1 S2 2.9 and this is 5.1. Now, we can say that 2.9 S1 plus 5.1 S2 less than 0, it is the feasible, it is the descent direction. That means, if we move from this point in this direction, then that would gives us the descent direction. Now, what is that direction at all? Now, this is the gradient of f, rather this is the minus grad f, because the functional value is decreasing further and further. And if I just take a tangent here, that tangent, the half space of that means this region would be the descent direction for f. That is the idea. Now, let us move to the next. What is the feasible direction? That means, we will calculate ST grad g. This is coming S1 S2 minus 1 minus 1. That means, we can say that minus S1 minus S2 lesser than 0, this is the feasible direction. Now, what is the usable direction then? Usable direction is that direction, that means that set of x1 S1 S2 which satisfies both the conditions together, that is 2.9 S1 plus 5.1 S2 lesser than 0, that is the descent direction, and minus S1 minus S2 less than 0, that is the feasible direction. Which direction it could be? This is the, this direction is the, this direction is the usable direction, give as said by the Zaudensik. All right. What is this direction then? This direction would be nothing but this cone. That is why this cone is being said as the cone of improving feasible direction. Clear? Now, whatever thing I said numerically, same thing we will just translate in mathematical form, that we will say that we will find S for getting the usable direction such that ST grad f is less than 0, ST grad g is less than equal to 0. All right. Now, if I consider one artificial variable, but how to solve it mathematically? That is why we are formulating a we are formulating a problem, an optimization problem, so that we can consider we can very easily consider the direction. Artificial variable alpha such that alpha is equal to max of ST grad f and ST grad gj. These are all gj at point x1, because we are x1 is our starting point. All right. Now, you see all the values are negative values. ST grad f is negative, ST grad g is negative. That is why alpha is negative here. Once alpha is negative, what is our target? Our target is the process has been designed in such a way that if we just move from a point x1, then we will move to the that direction, so that if I just move in this direction, then there is a chance that if I take a lambda k such that I will be out of the feasible space. That lambda k should not be that, so that I am out of the feasible space. Always I want to be within the feasible space. That is why select a suitable lambda k, so that we will remain in the next, if this is x2 for us, then we will remain within the feasible space. That is why we will try to remain far from the boundary of the constraint. That is the idea. That is why we will try to maximize alpha. That means we wanted to say that we will reduce alpha till it becomes negative. Thus, we can formulate a problem as minimize alpha such that St grad f less than equal to alpha, because alpha is the maximum of these two, and St grad Gj less than alpha for all j is equal to 1 to m, here also for all j. Alright. This is the problem. That means that find S such that this is being satisfied. That is why finding out the visible direction is not difficult for us, because that direction we will search which will satisfy this optimization problem. Okay. Let us use this one after doing certain modification. Now, you see, one thing is that we are interested about the direction S, not about the magnitude S, is it not? Because this is the direction we are looking for, not looking for the magnitude of the moving direction. That is why always we will try to normalize S by putting Si is equal to 1. Rather, we can say that STS is equal to 1. That is the normalization process, we can do it. Otherwise, if we consider ith component, how many components of S would be? S would be, will have n number of components. That's because we are moving in the design space where n number of, that is n dimensional space, because the number of decision variables are n. That is why we wanted to consider STS equal to 1, otherwise we may consider SI is in between minus 1 and 1. Then the advantage of considering this constraint is that we can bound this feasible region, otherwise this space may be unbounded for certain case. Alright. Either we can consider this or we can consider this. This is not being considered because always it will give you a quadratic function, but it will give you a linear function. Alright. That is why we are considering this. Now, we are doing certain modification for this problem. Let me just write down this modification in the next. Minimization alpha subject to St grad f less than equal to alpha, St grad Gj less than equal to alpha for all j is equal to 1 to m, and we have considered the ith component, all components of S is in between 1. Now, we are modifying this problem by considering another variable beta is equal to minus alpha. If we just do that, we are getting another problem. Just see, minimization of minus beta subject to St grad f plus beta less than equal to 0, St grad Gj plus beta less than is equal to 0, and Si in between minus 1 and 1. What is the advantage of considering that? Because you see, this is a linear function, these are all the linear functions. What are the decision variables here? Decision variables are Si's, because we wanted to find x, S, that is the feasible direction. Now, alpha is the negative value, that is why we wanted to impose that the decision variable, that is one of that is beta, that must be positive. That is why this can be considered very nicely, that beta is positive here. Now, there is another modification. Zaudenzik suggested that for the constraint set, the cone of the improving feasible direction, he wanted to capture the angle in between that. That is why he has introduced another term in the constraint set, that is theta j for all j, and this theta j is being named as the push factor. Rather, this is capturing this angle between the angle of the cone. Now, in general theta is always positive, because if theta j is negative, is not possible, because always it is acute angle for us. Not only that, theta j can be, if it is equal to 0, then it is a tangent altogether, and always we are considering theta j greater than 0, and by default we are considering the theta j equal to 1 in each case. Otherwise, we can consider it as a variable, and we can consider as a. Now, for finding out the usable direction as a whole, we can say this is the optimization problem we have to solve at each iteration. Now, this can be further be modified with another modification. Let us see, so that we will get a function where SI is not even negative value. We wanted to have a positive value here again, because here SI is coming negative, and as we know, for the linear programming problem, the simplex algorithm works only if the non-negativity constraint we have to ensure. That is why let us consider another variable Ti is equal to Si minus 1. All right. Then, since Si is in between minus 1 and 1, Ti would be in between 0 and 2. All right. No, rather it is 1 minus S. Ti would be is equal to Si would be is equal to Ti plus 1. All right. In the similar way. Now, if this is so, if we just write down this, if we write down this problem again, this problem is being formulated in this manner. Find T1, T2, Tn in place of S1, S2, Sn, which minimizes minus beta subject to, if we just elaborate here, we are putting Ti is equal to Si plus 1, Ti is equal to Si plus 1. Yeah. If I just put Si plus 1, then we are considering as T1 del G1 by del X1 plus T2 del G2 by del X2 Tn, no G1, because first constraint we are considering Xn plus theta j beta less than is equal to summation I is equal to 1 to n del G1 by del X I. All right. Because we have considered Si is equal to Ti minus 1. Now, this is for all j, that is why let me just put j here. For all j from 1 to m, and for the objective function we are getting one constraint only. Less than is equal to summation I is equal to 1 to n del f by del xi, and Ti is in between 0 and 2. What else? Beta is greater than 0. This is the linear programming problem. That is why that would be considered as the usable direction. That is all about the usable direction. If I go back to the methodology, that is the Zaudenzik method for feasible direction. This is the process for us. Start with an initial point x1, evaluate fx1, gjx1, and if gjx1 is lesser than 0, that means we are in the interior point. and the feasible direction SI would be is equal to minus grad of f, and we have to normalize SI and we have to go to the step 5 if we are in the interior point. But if we are in the boundary point, then we have to find out a feasible direction by this process, that is minimization of minus beta ST grad f plus beta less than is equal to 0. In this way we are finding out there is another constraint, that is the beta is greater than 0. That's we are getting the usable direction. All right. Now, whatever direction we are getting, if this is almost equal to 0, then we can stop our iteration. That means there is no further possibility for improvement. But if we see that it is not equal to 0, rather if beta star is less than epsilon, epsilon is a very small positive value, then we will stop iteration, we will declare that the corresponding xi as the optimal solution. If it is not so, then we need to go to the next step, because we have to find out a suitable direction, because how we will find out lambda I and SI in such a way that we can move to the next point xi plus 1, and we will do the process. How? We will find out the functional value at this point, and if the difference of the functional value, rather the rate of difference is very small, and if xi's are very close, the norm, that is because these are all the vectors, these are very close to each other, then we will declare that one as a optimal solution. Otherwise, we have to move to the, we have to go to the next if it is not optimal, because we have to repeat the process again and again. We will see whether x2 is in the boundary of the feasible space or not. If it is in the boundary of the feasible space, something is there. If it is not in the boundary of the feasible space, now if it is in the boundary of the feasible space, then we have to repeat this process from step 2 again. But if it is in the interior point, we can proceed further with this step length and we will move to the next. And I have prepared one problem for you to understand in a better way. Just look at this. This is the problem for us, fx1 x2, and this is the nonlinear problem, x1 square plus x2 square minus 4x1 minus 4x2 plus 8, and g is this one. Now, we are starting the process from 0 0. Since 0 0 0 0, the point is very much in the feasible space. Not only that, the point is in the interior point, it is not the boundary point, because with this point it is not being satisfied with equality sign. If we consider the starting point as 2 1, then certainly it is the boundary point, and we have to do some processing, so that we are not out of the feasible space. Otherwise, we can remain with the next. Just you see what we are doing. As I said, Gj(x1) is lesser than 0, and we are getting the next direction as 1 1, because we are considering the descent direction of f, that is 4 4, we are normalizing it and we are getting the direction 1 1. Our next task is to find out which one. We are trying to move from x1 to x2 in such a way that x2 is equal to x1 plus lambda 1 s1. S1 is this one, x1 is given 0 0. What is lambda 1? We have to just find out in the next. For doing that, as we did for the unconstrained optimization problem, here also the same thing. We will do the same, we will just find out the function f, and we will see for which value of lambda f is minimum. That is why we are getting if lambda is equal to 2, then f is minimum. But if lambda equal to 2, then the next point x2 would be is equal to 2 2. Just look at the constraint. If it is 2 2, then I will be out of the feasible space. That means G1 is violated, that is not accepted. That is why what should be done? We have to reconstruct lambda 1, we have to suitably select lambda 1 in such a way that G1 x2 will be at the most on the boundary, alright. But here G1 x2 is coming greater than 0, it is not accepted. That is why we will select lambda in such a way that it is in the boundary. If this is so, very easily we can select by considering g x 2, by substituting x 2 in g, we will see the lambda 1 value is coming 4 by 3. That is why we can say x 2 is equal to 4 by 3, 4 by 3, which is nothing but x 1 plus lambda 1 plus s 1, all right. Now, we will select whether x 2 is optimal or not. Now, we see the difference of f x 1 and f x 2, that is not very low, that is very high, that is not acceptable. That is why x 2 is not cannot be considered. Not only that, norm of difference x 2 minus x 1, that is also very high, that is not very small value. Here we are considering FCLN 2 and FCLN 3 as a pre-assigned very small positive value, maybe 0.0001 and 0.0002, even we can consider the same value. That is why you see, not only that, once we are reaching to x 2 is in the boundary, on the boundary of the feasible space, because it is satisfying the constraint with equality sign. That is why we have to select the next process, the next S2, that is the next direction, in such a way I should not be out of the feasible space. That is the check for us, because if you see, I am in the boundary, there is every chance that I will be out of the feasible space. That is why always I will try to select the direction that is usable direction. That means that lie within the cone of improving feasible direction. That is why in the next case what I am doing, I am selecting the usable direction with that problem, with that linear programming problem, as I explained you before, that is minimize minus beta subject to the T1, T2. I just showed you the that is the this one, this the whole linear programming problem I am writing again for this one, and we are getting this linear programming problem, and we are getting the beta star is equal to minus 4 by 10. Now, once beta star is equal to minus 4 by 10, as we have considered t is equal to s I plus 1, that is why s could be t1 star minus 1, t1 star from here we are getting 2, t2 star we are getting from here 3 by 10. That is why my next, that is s2, could be is 1 minus 0.7. That means this is the usable direction in the next. That is why from x2 I can move in this direction. Again the problem is still there, what should be the step length? That is why we have to adopt the next process, that is lambda 2. We have to find out lambda 2 in such a way that I will remain within the feasible space. Not only that, we are selecting the descent direction, that is the usable direction. That is why we are selecting lambda 2 in a suitable manner, so that I remain within the usable direction. If I just repeat the process as we did for in step 2, the similar way we are selecting lambda 2 as 0.134, then we see that g of x 3 is within the feasible space, and for this x 3. That is why this lambda 2 is quite acceptable for us. That is why we can move to the next x 3. In this way, if we just proceed further and further, after few steps we can see the optimal solution is coming this one, and we will get the functional value as 0.8. And this is the method where we are using the method of feasible direction. There is another alternative method is also there, that is the Rosen's gradient projection method. Now, today I am not going to detail that method, but either of these two methods you can use it. The beauty of this method is that we can very nicely we can adopt a search iterative process in such a way that always we will remain within the feasible space, and that this method is very popular method. That is why I discussed this one, and with this today I am concluding. In the next I will discuss few methods on indirect searching technique for constraint optimization problem, that is penalty function methods in the next. Thank you very much for today.